Ever wondered how your phone's GPS figures out the absolute fastest route? Or how a video game makes a character's jump feel just right? Well, the secret sauce is this hidden language that's all around us, governing movement and direction. Today, we're going to decode that language, the language of vectors.
All right, let's imagine you find an old treasure map. It says the treasure is buried just 1 kilometer from where you're standing. Awesome! You grab your shovel, you're ready to get rich, but then you stop. 1 kilometer? In which direction? North? Southeast? All of a sudden, that map seems kind of useless, right?
Exactly. Distance by itself is going to have you wandering around in circles. To find that treasure, you need the full instruction, not just how far to go, but which way to go. And that one simple idea, that's the key to everything we're about to get into.
So this brings us to a really important distinction in, physics and math. We've got 2 different ways of talking about quantities. One is just a simple number, and the other is that complete instruction we needed for our treasure map. And you can see it laid out perfectly here. On the left, we've got scalars. They just tell you how much of something there is. That's the magnitude. So think, 20 meters of rope or a temperature of 70 degrees. Simple. But on the right, we've got our hero for the day, the vector. It gives you both magnitude and direction. It's not just 12 meters, it's 12 meters at 20 degrees north of east. One is just a number, the other is the whole instruction manual.
Okay, so let's just make it official. A vector is a quantity that has both of those things, magnitude and direction. Honestly, the best way to think about it is as the ultimate instruction. It doesn't just tell you how long the trip is, it gives you the entire roadmap in one tidy little package.
Okay, so vectors are complete instructions. But what happens when that instruction is some kind of complicated diagonal path? I mean, how do we even work with that? Well, the secret is to break it down into a language that's way, way simpler to deal with.
And this is the big idea right here. Any journey, I don't care how diagonal it is, can be described as just moving some amount horizontally and some amount vertically. So instead of one complicated step, we can think of it as 2 incredibly simple ones. And trust me, this makes all the math so much easier.
We call these simpler paths components, and finding them is a super simple 2-step process. First, we figure out how much of the trip was in the east-west, or what we call the X direction. Then, we do the same for the north-south, or Y direction. That's it.
This is such a brilliant way to put it. A component is basically the shadow that a vector casts on an axis. It's the effect of that diagonal movement, but only in the pure horizontal or pure vertical direction.
Okay, theory is great, but let's make this real. Let's say a person walks 400 meters at a 30-degree angle, kind of northeast. So the real question is, how far east did they actually travel, and how far north did they actually go?
And when we run the numbers, boom, there's our answer. That single 400-meter diagonal walk is the exact same thing as walking 346 meters due east and then 200 meters due north. We've translated one complex instruction into 2 really simple ones. This is the key, because now we have a way to handle any vector, no matter what direction it's pointing.
Now we get to the really powerful part. Because if we can break vectors down into simple pieces, that means we can also add them together. We can take a long, winding trip with a bunch of different legs and find the one single direct path, the ultimate shortcut.
So let's put this whole idea to the test with a new challenge. We've got a boat that takes a journey with a whole bunch of different turns. It ends up somewhere new, but it definitely did not take a straight line to get there. So according to the ship's log, this trip was all over the map. First 2 kilometers east, then 4 north, then it goes back 3 west, and finally 2 south. I mean, just looking at this list, it's pretty much impossible to just picture where the boat is now compared to where it started.
So this is the real question we want to answer. If you could have just gone in a perfect straight line from the starting dock to where the boat ended up, what would that path be? What's the distance and what's the direction of that shortcut?
And here's how we turn all that chaos into simple order. We just add up all the east-west movements and all the north-south movements completely separately. So in the east-west column, we've got a +2 and a -3, which gives us a total of -1. And in the north-south column, a +4 and a -2 gives us a total of +2. It's really that easy.
So after all that sailing around, the boat's final position is just 1 kilometer west and 2 kilometers north of where it started. We found the components of our shortcut vector, what we call the resultant. But wait, that's not the full answer yet.
Now, using those 2 simple components, 1 kilometer west and 2 kilometers north, we can figure out the true straight-line distance. That shortcut path, as the crow flies, has a length, or a magnitude, of 2.24 kilometers.
And for the final piece of the puzzle, the direction. It comes out to be 63.4 degrees north of west. So, the complete answer, the single vector that replaces that entire winding journey, is 2.24 kilometers at 63.4 degrees north of west. We did it. We found the shortcut.
So look, this isn't just a neat trick for treasure maps and boat trips. This method of breaking down and adding up vectors, it's a fundamental tool that's used all across science and technology. It's really a language for describing how our world works.
I mean, seriously, just think about it. Your phone's GPS, it's constantly calculating vectors to find you the shortest route. The physics in a video game, that's all vectors, figuring out how a character jumps or how an object flies through the air. From weather models tracking wind to engineers calculating forces on a bridge, this stuff is truly everywhere.
So the next time you use a map or play a game or even just feel the wind on your face, try to remember what's going on under the hood. You're living in a world that's built on vectors. And once you start to understand their language, you start to see all the hidden instructions and invisible forces that are shaping everything around you. The only question left is, what are you going to see differently now?